Okay, we gave you some background on what's happening on a kind of a regulatory policy standpoint. Now we're going to give you some background just simply about nitrogen and how it behaves, because if we're going to make our best choices on how we manage nitrogen fertilizer and nitrogen resources, it's really actually important to understand what nitrogen does in the environment. And so this is kind of the part of the program that we're really drawing from our Nitrogen Smart program. We want to cover some of this before we have our nutrient management specialists get into some more specifics about nitrogen management. So I'm going to try and do this kind of quickly. I think most of you realize nitrogen in and of itself not only is not a contaminant, it's what you're breathing into your lungs. It's 78% of the atmosphere. Above every acre of land, there's roughly 117,000 tons of nitrogen in the atmosphere. Now, of course, that's non-reactive nitrogen, N2 gas. Doesn't necessarily create a problem, but that certainly means there's plenty of nitrogen out there to draw from. Soil organic matter, which you can think about how many percent organic matter you got in your soil, has roughly 1,000 pounds of nitrogen for every 1%. So pretty typical to have maybe 3% organic matter. That means you've probably got 3,000 pounds of nitrogen in your soil with your 3% organic matter, or maybe higher if you got a higher percentage of organic matter. Now, of course, that's not reactive nitrogen. That's locked up in some kind of organic molecule. However, a percentage of that does what we call mineralize or decompose basically on an annual basis and release for the growing plant. And so the potential is there, and there certainly is a lot of nitrogen in our soils. Nitrogen, as I think most of you realize, is typically the limiting nutrient in most of our ecosystems. It's a primary component in protein. And so, it's because of its mobility in the environment, it's just simply not out there in large quantities in a reactive form that can be picked up by plants. And so, I talked a little bit before about limiting nutrients in water. The limiting nutrients for plant growth in a lot of cases are nitrogen, particularly when it comes to grasses like corn. The more nitrogen we put on, the more potential it has to grow. Plants are roughly 1 to 6% nitrogen. Really varies depending on what the plant is. The two inorganic forms of nitrogen that are of primary concern to us for plant nutrition are ammonium and nitrate. Ammonium is a cation, nitrate is an anion. What's important for you to realize is our soils are negatively charged, so clay particles in the soil. Clay is actually, if you look at it under a microscope, is a plate. And so if you consider it as to be like one big continuous plate, that would just be one big continuous plate, but it's not, it's broken apart. And so every place where it breaks on the edges creates negative charges. And so from that standpoint, positive ions like ammonium will adhere to the soil. That's what we consider cation exchange capacity. However, negative does, it repels itself. I think most of you have done that with a magnet before. And so when the nitrogen is in the nitrate form, it is no longer held in the soil. It is a misnomer that nitrogen has to be nitrate for the plant to pick it up. Most of the nitrogen that's picked up by the plant is nitrate, and that's because nitrogen converts itself to nitrate through biological processes in the soil. It moves with the water. As the plant's taking up water, it's picking up nitrate out of the soil. However, plants will take up ammonium just fine in the same way they're picking up potassium and other cations off the plant. Not of a lot of importance, but I think it's worth noting. I will occasionally hear somebody say, well, the nitrogen's got to turn into nitrate before the plant picks it up. Well, that's not really true. Because of the microbial activity that turns nitrogen in the soil into nitrate, microbes, as you all are aware, are active most when it's warm and wet. So, just think about if you eat supper and you leave the food sit on the table, it's probably wet and it's probably warm, and you'll get microbial activity if you leave it sit there until morning or the next day. Same thing with the soil. When it's warm and wet, we see that microbial activity happen. And so nitrate is highly mobile, as I said, because it does not absorb to the soil particles. Ammonium is not as mobile. However, ammonium turns into nitrate and then it becomes mobile. It's one of the main reasons why we're not really high on using cation exchange capacity for nitrogen recommendations, because the nitrogen doesn't stay as a cation very long. It turns into an anion, and then it doesn't really matter what the cation exchange capacity is at that point. Nitrogen is mobile in the plant. So we will see nitrogen going to the point that's growing. The plant will rob itself if it doesn't have enough and move it to those parts of the plant. So the deficiencies in nitrogen will show up in the oldest plant material first. And this kind of shows some pictures showing nitrogen deficiency. So you can see where it's limiting. You can see dead leaves going up. And then where it's in excess, you can see how much extra green it is. Typically speaking, though, we do want to point out that it's normal to have dead lower leaves senesced. There's not a lot of sunlight down there. Those leaves don't do much for you. If the corn is green all the way to the soil surface, you probably have too much nitrogen on, because it is pretty normal to see some dead leaves on the lower part of the plant. One of the big problems with corn is it does not penalize us for putting on too much nitrogen. Most of the other ag crops that are grown commercially in the United States have a problem. I bet you all know what happens if you put on too much nitrogen on small grains. It ends up flat on the ground, right? And if you put on too much nitrogen on sugar beets, the sugar content goes down and you don't make any money. So the beet producers have to be very careful about how much nitrogen they put on. If you go to the south, if you put too much nitrogen on cotton, cotton will grow 10 feet tall and never produce a cotton boll. You'll have nothing to sell at harvest time. And so most of our agricultural crops actually penalize us for putting on too much nitrogen. Corn doesn't do that, and that's kind of led to some of our problems over the years, because excess nitrogen in the soil for corn, it just simply walks away from it. Doesn't need it, doesn't care one way or another. And so that's kind of caused some of the problems we've had in the past. Let's talk a little bit about transformations. As I said, nitrate is really where the problem lies, is kind of our focus here. Nitrification happens in the soil. Microbes in the soil are changing the ammonium into nitrate in the presence of oxygen. Denitrification is the loss of nitrogen out of the soil. Also happens when the nitrogen is nitrate, and so it's important to recognize our two most significant loss processes of nitrogen involve conversion of the nitrogen to nitrate. However, this happens when there's no oxygen in the soil, and so it's really when the soil has become completely saturated. If this process is complete, it turns back into N2 gas, which is what we're breathing into our lungs, not an environmental contaminant. If it's not complete, it turns into NOx, which is considered a greenhouse gas. That's a topic for a different meeting that's not here today, so we're not going to talk about that. But it is important to realize nitrate is kind of where we lose most of our nitrogen. Now, for you guys in the southeast Minnesota, because of the nature of your soils, we typically don't stay saturated for really very long. There's places and there's some soil types, and you may get low on the landscape by a river and some things. There's going to be areas, but in general, this is the big issue when we get into south central Minnesota with our glacial till soils, not so much with the loess soils in the southeast. So nitrate, as I said, is negatively charged, and so it does not attract itself to soil particles. So if there is water movement through the soil and it is free, it is able to be leached or moved down into the soil profile. And of course, most of our corn's rooting about 3 feet deep. So if it goes down deeper than about 3 feet, it's probably lost. As I said, this is microbial, and microbes want it to be warm and moist. We actually see the inflection point of changes in nitrification happening at 50 degrees. We don't any longer recommend application of nitrogen in the fall for the majority of southeastern Minnesota. In the parts of the state where we do still say it's acceptable, that we do say don't put it on before 50. You can see at 50, the rate of nitrification increases rapidly. It's kind of worth noting, and I don't have a complete data set for Rochester, however, like at Waseca, which is roughly, the same latitude as us, the average day we hit 50 degrees soil temperature is May 1st. And so that's kind of the point at which we start seeing the rapid conversion of the nitrogen in our soil to nitrate. Nitrification inhibitors, you know, now that we really don't recommend fall application here, maybe not quite such a thing. Dan will talk a little more about that. The important thing to know about nitrification inhibitors is it's never really, not really a case of whether they work, depending on how you define work. If what you say is they delay the conversion of nitrogen, of ammonium into nitrate, they do work. Is did they work long enough and at the right time to make a difference for what we're trying to do? So did they increase yields? Maybe not. Did they keep nitrogen out of the water? Maybe not, you know, but they do work as far as slowing the conversion of ammonium to nitrate. So, you know, for that reason, you know, most of the application windows in southeast Minnesota, we're not particularly high on these. If you've got a site that's really that prone to nitrate loss, you're probably going to see much bigger benefit for split applying nitrogen than you are for using these products. However, they could be a tool. I already mentioned mineralization, the conversion of nitrogen out of your soil organic matter. You know, this happens, it's microbial, and so it happens as long as the soil temperatures are warm and there's adequate moisture in the soil. It has great potential on an annual basis. We don't really make any separate recommendations on how we manage nitrogen based on your soil organic matter. And one of the primary reasons for that is if you look across the state, the places we have the highest levels of soil organic matter are some of the wettest spots on the landscape, and that's why the organic matter has gone high. And so the productivity potential in those areas is actually typically pretty low because of how wet they are. And so we certainly don't say, well, if you got higher organic matter, you need less nitrogen, because in some of those spots, well, you don't have as good of a crop either. So it's really a complicated situation. So I already mentioned denitrification and the fact that that happens when the soil is completely saturated. This typically takes about 24 hours before it gets going. You know, those microbes aren't in the soil in giant abundance at any given time. There's always just some little population waiting there for conditions to be right. And so typically speaking, we don't see rates of denitrification being very significant until about 24 hours after the soil's been saturated. So again, think about southeastern Minnesota and your lush soils. How often are the soils saturated for 24 hours? And then longer after that, you know, unless we've been getting rainfall after rainfall after rainfall, which does happen sometimes, but in general, probably not going to be as big of a problem as it is in other parts of the state. However, it is worth pointing out, well, first of all, we don't see this as a really big problem when the soil temperatures are cold, again, because it's microbial and microbes don't do a lot when it's below 50 degrees. However, when the soil temperature is getting close to 80 degrees, if it stays saturated for 10 days, you can lose almost half your nitrogen, and that's just off into the air, not into the water. Urease inhibitors, and the main reason I wanted to throw this in there is that, you know, just for the sake of not getting yourself confused, that nitrification inhibitors are intended to slow down or stunt the conversion of ammonium to nitrate. That's products particularly like nitropyrin, like N-Serve or Instinct on manure. Urease inhibitors are for urea, and that's products like Agritane and then a whole bunch of other products, there's generics and so forth. Those are intended to stop or slow the volatilization of ammonia off of the urea prill. And so very, very different things that are going on. So, you know, really from a water quality standpoint, urease inhibitors really probably aren't as much of a deal. They're a big deal as far as how you're managing your nitrogen efficiently on your farm, but they're not going to have a big impact on water quality because the loss process there is up into the air, not into the water. A little bit about leaching. I know there's not a lot of drain tile in Southeast. It's getting to be a little bit more, but it's really valuable to look at our research on drain tile because, you know, when we're talking about shallow groundwater, it all behaves sort of the same. It's very difficult to pull a water sample out of shallow groundwater. It's very easy to pull a water sample from tile. You just hold a cup under it and collect it and then take it into analyze it. And in general, because nitrogen behaves the same everywhere. While the soil types are different and some of the characteristics are different, the nitrogen aspect is behaving the same. And so we can look at, for instance, some of the research that's been done at Waseca and kind of compare what that would look like or what those concepts are and how they apply to the Southeast. Roughly speaking, we'll move nitrate about 5 to 6 inches in the soil for every inch of excess drainage. So if you think that the water, you know, if the soil's at basically at field capacity, it can't absorb any more water, that extra inch of precip percolating through the soil is going to take it down about 6 inches. And so, you know, if you think about, you know, where your application was, if you're dealing with urea and it's close to the surface, you know, it's got 3 feet to go. If you put it on, either put on anhydrous or you did some kind of deeper incorporation, maybe it's got 2.5 feet to go, something like that. You can think that, roughly speaking, it takes about 5 to 6 inches of excess precipitation to move it to where it's gone below the rooting zone of the corn, okay? And so, as far as, you know, strategies to minimize the leaching, obviously, you know, don't put on too much. The application closer to the time the plants need it, you know, in general, your corn reaches its rapid growth phase about the first week of June. And so that's when it really needs the nitrogen. Any period of time that it's out in the field when the corn's not growing and using it is vulnerable. So the closer you can get to the time it needs to use the nitrogen, the less risk there is because it's just simply not out there. You know, it's one of the strategies why split application makes sense in some situations, but it's also one of the reasons why, you know, split application doesn't always work in terms of increasing yield, because if you don't lose the nitrogen, well, it's still there, right? You know, so then it didn't make any difference. Occasionally you'll hear people talk about runoff. You know, we got nitrogen running off the field. Actually, the amount of runoff of nitrogen is very, very slight. That's really not much of a thing. And it's mostly associated with soil erosion and what might be tied up in the soil that's taken off. So it's really not a significant factor. I just kind of wanted to mention that. People will talk about atmospheric deposition. This is obviously not something we credit. It just kind of happens everywhere, but nitrogen is fixed by lightning in thunderstorms. And so the deposition of nitrogen from rainstorms is roughly about 10 pounds per year. There will be a little bit associated with blowing soil particles, not a lot, but that can be a factor too. Obviously, it's not calibrated across the landscape, so it's not something we can really manage to any extent. Obviously, fertilizers are really the most important thing that we're talking about, as well as applied manure. So I guess a few things related to, I want to, before we get into more specifics about nitrogen management, which we're going to do later in the morning, I want to point a few things out. So as I said, we used quite a bit of the data from the drainage plots at Waseca because it really illustrates our points. So this is a long-term study. Giles and Jeff worked on this. This was published in 2011. And so we got the crop rotation of corn, soybeans here. I want to point out a couple things. This is the total, this is 4 years of nitrate leaching. So if you want an annual one, divide it out. Where we grew soybeans and applied no nitrogen, we lost about 10 pounds of nitrogen per acre. Where we grew corn and we applied no nitrogen, we lost about 10 pounds per acre. How did that happen? You didn't put anything on it. Came out of the soil, okay? So if we applied what we considered a recommended rate, that number really didn't jump up a lot. It's more like 15 pounds per acre. So in that particular case, we're looking at, roughly speaking, about 2/3 of the nitrogen that came out of the tile lines when we were doing our best to manage nitrogen didn't come from the fertilizer. That's pretty much an artifact of our annual cropping system. So as I said before, nitrogen is going to mineralize out of soil organic matter as long as the soil is warm and moist. We reach physiological maturity of our corn crop, roughly speaking, about Labor Day or so, okay? the soil temperature is not cooling down to 50 degrees until the end of October. So we are continuing to mineralize nitrogen out of the soil organic matter post-growing season of the crop. That's just kind of the way annual crops are. And so a lot of our evidence shows, and this in particular, when the crop is growing, it's not going to leave this behind. What's being left behind is what's mineralizing after the crop is done growing. And as kind of more evidence to this was some research that was done at Lamberton many more years ago. In cases where we had alfalfa or perennial grasses, you can actually see that the loss numbers they're not zero, but they're almost zero. You're down to 1 or 2 parts per million. So as long as there's something alive and taking up that nitrate out of the soil, we would see that those numbers go down to zero. It's one of the reasons why alfalfa production is really important as far as trying to keep the water clean and therefore the livestock industry, because that's the only sort of place we've got to move our alfalfa to. But it's also one of the reasons why cover crops show such great potential for dealing with this problem, because if we can get something alive and growing after the crop is done taking that nutrient out of the soil, we potentially could arrest this in place and leave it there until next year when the crop is up and growing. This is some data from Giles and Jeff. This was actually collected at the Lawler farm, and there's really 2 points I want to show here. One is where they applied zero nitrogen. This is residual soil nitrate from soil samples after harvest. There's still roughly 50 pounds per acre of nitrogen left out in the field. And again, no nitrogen was applied, and there's still 50 pounds. The only place it could have come from, guys, is from the soil organic matter, right? In this particular case, the optimum yield was attained at about 90 pounds, and you can see that the residual nitrates there are still only slightly higher, maybe about 55 pounds. However, in this case, if we over-fertilized, if we put on more than what the crop needed, it was pretty much pound for pound left behind in the field. And so that's really where this lies, is we need to be trying to really nail down exactly what the crop needs, because we know that if we over-fertilize, if we're putting on more than what the crop wants, it's probably just going to leave it behind in the field. And so that's really kind of the focus. It also points out, we'll hear people say, well, you're only worried about maximizing return. That in essence, the point where we maximize return is really not causing a great environmental consequence. It's when we go beyond the point that's maximizing return that we start leaving it out in the environment. And this is just some other data showing kind of the, again, this is drainage, but it's the same concept and it's important. The yellow bars are rainfall and the red bars are drainage through the drain tile. This line is growth of corn. So you can see once the corn starts growing and taking water out of the profile, the drainage shuts off. And the same thing happens here in the southeast. You may not have drain tile, but the loss of water down into the water table or below the rooting zone really shuts off when that corn really gets growing. And so our vulnerable period is really right here, kind of in advance of that crop getting going primarily in June. And if you look at the data from Waseca, again, this is drain tile. However, it's the same concept. You see that most of the water is lost in April, May, and June before the crop really gets growing. Most of the nitrogen is lost. It's a little bit offset, but again, it's mostly April, May, and June. And so if you think about the physics I told you before about nitrate moving roughly 6 inches with an inch of water, if you did a fertilizer application the first week of April, is it able to get out in April? Unless you had some catastrophic flood, the physics says it didn't move that far. That's not the applied nitrogen that you put on that's going through that water. That's what was left over after the cropping season last year, or the mineralized nitrogen from the previous year. So the last point I want to make before we move on here is a lot of the techniques and the strategies that are being suggested for reducing nitrate loss to the environment could end up being very expensive. Better nitrogen fertilizer management not only is it the cheapest thing we can do to address this, it actually puts money in your pocket. Because if you're maximizing yield at the exact right nitrogen rate you need to be applying and the way you need to apply it, you're actually making money off of that practice instead of it costing you money. And so as an industry standpoint, before we start spending a ton of money on some of these other practices, that are intended to kind of get it out once it's already there, we need to do the best job we can do to manage nitrogen fertilizer, nitrogen manure inputs, and get the best bang for our buck out of that, because that makes us money instead of costing us money. And so that's kind of really the point I want to finish with there. So I will point out that the entire NitrogenSmart training is available as an online course. So if you want to go to our website, we call this a Z-link, z.umn.edu/NitrogenSmart. We have online training, both not only for our fundamentals session, we have a 3-hour session on manure. We have a 3-hour session called a deep dive into the 4 R's. We have a 3-hour session on adapting nitrogen management to climate. And hopefully very soon, we're going to have a 3-hour session called reducing nitrate loss to water. Maybe by next year, we'll also have our 1-hour sessions on variable rate nitrogen and using biologicals there. I am always available for you to call, email, whatever. I know some people, depending on what county you're in, you got a local educator here in Olmsted County again. We got educators in Houston and Fillmore, but you may be in a county that doesn't have a local educator. You're always welcome to call me. No, you're always welcome to call me. That's fine. And so again, I just want to wrap by saying thank you to Minnesota Corn for sponsoring this meeting today. I am more or less done. I'll come back at the end of the day and help moderate the farmer panel. But with that, I'm going to bring up Kevin Keener from Department of Agriculture, and he's going to talk about some recent work that they've done on how old is the groundwater in southeast Minnesota. And while we're transitioning, if anybody has any quick questions, I'd be happy to answer those.